Okay, everyone. Um, what I'd like to do now is to derive the time-independent Schrodinger equation from the full Schrodinger equation using a technique called separation of variables. All right? This is worth paying attention to because we're going to use this trick one or two more times in our class. And you'll see it again in most of the upper level physics classes that are coming down the pike, right? So, although the math itself is not the most important thing for us, it's worth paying attention to this trick. All right, let's suppose we're in a situation where our wave function can be written in separable form. Okay? We know that's only true if the potential energy is time independent. But nevertheless, then if that's true, then we can substitute this back into the wave function in the following way. So now we'll have, looking at the full wave equation, we have I h bar times the time derivative of psi of x and t is equal to minus h bar squared over 2m times the second derivative with respect to position of the wave function plus the potential energy times the wave function. So making that substitution, we have I h bar times time derivative of phi times psi is equal to minus h bar squared over 2m times second derivative with respect to position of psi times phi plus u times psi times phi. Okay? Now, notice that the phi function depends on time, but the psi function does not. So we can rewrite the first term as I h bar, excuse me, times psi times the time derivative of phi. I'll write it like that. On the right-hand side, we have minus h bar squared over 2m times the second spatial derivative of psi times phi, but phi is position independent. So we can bring it outside of the differential as well. All right. So we substituted into Schrodinger's equation, and now we're going to divide both sides by the wave function. Okay? Let's see what we get when we do that. So when we do that, and writing the wave function in this form, we have I h bar psi phi dot divided by psi times phi. And this is equal to minus h bar squared over 2m phi psi double prime divided by psi times phi plus u times psi phi divided by psi phi again. Okay, and you can see so that some terms cancel out. Allowing us to rewrite this in the following way. I h bar times phi prime divided by phi is equal to minus h bar squared over 2m times psi double prime divided by psi plus u. Okay? Oh, well, that was a little bit of work. It's not clear that we've really done anything right, but when we take a look, you'll see there's something really important. If we look at our equation now, and if you look at the left-hand side of the equation, you'll see that the left-hand side of the equation only depends on t. there's nothing in that equation that depends on x. So this is position independent. Or maybe more clearly, we could say it depends only on t. On the right-hand side of the equation, there's no phi. And so the right-hand side of the equation depends only on x. Okay? So that's kind of interesting. What's even more interesting is that if you consider this carefully, you'll see that because these two terms have to be equal to each other for all values of x and t, that means that both terms have to be constant. That is, the right side and the left side are independent of x and t. Here, let's think about why that's true. Suppose we pick a particular moment in time, t equals 0, or any other time. Then the left-hand side of the equation must have a single constant value, right? On the right-hand side, we have a function that is apparently depending on x, but the right-hand side has to equal that constant term no matter what the value of x is. So actually, the right-hand side taken all together cannot depend on x. We have two terms that each might depend on x, but the sum of them has to be independent of x. Otherwise, the equation won't be true for any specific time for all possible values of x. Likewise, if we pick a particular position, we see that the left-hand side has to be equal to the specific value of the right-hand side for that particular position for any value of t. So the right-hand side actually cannot even depend on t. So both the right-hand side and the left-hand side must be constant. Okay? Because of that, we can break them into two terms, two equations, each of which is equal to a constant. So we could write this as I h bar phi dot over phi is equal to a constant, and minus h bar squared over 2m times phi psi double prime divided by psi plus u, that's also equal to a constant. Notice we've introduced a new term here, e, which here is just what's called the separation constant. We don't yet know what e is, but we do know that it's the same value for both equations. Now, let's take a closer look at the first one and see if we can rewrite it in a simpler way. Well, we can. Let's multiply through by phi on both sides, and we get I h bar phi dot is equal to e times phi, or phi dot is equal to minus I over h bar times e times phi. And of course, that's the first part of our result previously. This is the equation for the time-dependent part of the separable solution. Turning to the second part here, we can rewrite this as in the following way. By multiplying by psi on both sides, we have minus h bar squared over 2m phi double dot plus u times phi is equal to e times phi. And this is, of course, a statement of the time-independent Schrodinger equation, which we wrote a moment ago in this way. There we go. So what we've just done is to start with our full Schrodinger wave equation here, assume a separable solution, and then go ahead and plug it in. And what we found is that the Schrodinger equation, a partial differential equation in two variables, broke apart, in this case, into two ordinary differential equations in a single variable. Okay, this only works for separable solutions. That is, it only works for energy states. But when it does, it gives us this beautiful, simple answer. Let's stop here.